The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, first of all, a message I've been repeating for a couple of days. A reminder, there will be no office hour this afternoon. I have to attend a meeting, but if you do have questions, email me and I will get back to you as soon as I can. Secondly, I will be unavailable Saturday and Sunday. I will be where there is no internet. So if you have questions over the weekend, I probably won't get to them until late Sunday night or possibly Monday. Again, Monday is a holiday, no classes on Monday. Coming up tomorrow is going to be the review for this chapter, excuse me. And so then Friday, tomorrow, anyway, we'll review. And then your test will be on Tuesday, though you can take it anytime before then if you want. All right, eventually we're going to go on to section 11.6 and 11.7, wrap up the chapter today. Seems like a lot of material, but we're only going to look at one little concept in 11.6. Before we do that, I've got some questions from a student concerning going back to section 11.5, part 1. And this has to do with log notation. First of all, if we have the following expression, it looks like that, okay? So it says L in and then X in parentheses. This means the natural log of X, or log base E of X. If we were to say this in just letters, we would say Ln of X, which is the natural log of X, or log base E of X. On your calculator, there is a button that says Ln, and when you use that button, you are basically using this or this. You're saying, I want to take log base E, or the natural log of some quantity. So if you say Ln 3, you're wanting to take the natural log of 3. Okay, now let's see the other thing. Let's also look at the other notation, log of X, or log of X. Here, log, just log, stands for common log, or log base 10. So if we want the log of X, we're saying we want log base 10 of X. And again, to access that, we're going to use the key that just says log. Okay, so we've got this key on our calculator and this key on our calculator. The first one is log base 10. The second one is log base E. The second function key of log is 10 to the X, and the second function key of natural log is E to the X. Make sure that you're accessing the correct key that you want in a situation. Okay, moving on from there, we're now going to go to section 11.6. Give me a second here to set things up. So I want to make sure I've got the right screen accessed. Okay, so this is 11.6. And let's go back to a scenario that I did the other day where I said 2 cubed is 8, and 2 to the 4th power is 16, and 2 to the X power is, and I don't remember what number I chose. It was something between 8 and 16. It doesn't really matter for what we're doing here as long as it's something between those. I'm going to use 10, okay? So from that, we got 2 to the X equals 10. And then we learned to use logarithms to take an exponential equation like this and change it into log base 2 of 10 equals X. Or we could say X equals log base 2 of 10. Now, this is all logarithms, but most of us don't have a calculator that will allow us to enter that directly. So we need to use what is known as the change of base formula, okay? So the change of base formula. My writing is atrocious as usual. No surprise there. Okay, change of base formula. Okay, so that's the thing we're going to be looking at in section 11.6. And let's take this situation and let's figure out what the answer is. In general, the change of base formula looks like this. It says log base b of x equals log base a of x divided by log base a of b. Again, we're assuming that these are all real values, that a, b, and x are all acceptable values in the domain of the expression. All right, now, so log base b of x, the x goes up on top, the b goes down below, the x goes up above, the b goes down below, and then we change things to write base a. Well, what are we going to use for base a? We're either going to use e or 10 because we have those two keys on our calculator. All right. So using our example, we could rewrite this as log base 10 of 10 over log base 10 of 2. Okay. Now, using log base 10, I could just write this. Okay. I don't need to write the little 10s in there. They're implied. But if I go to my calculator, and I put in log of 10. So log of 10, close it up, divided by log of 2. Oops, pushed the wrong button there. Let's see, log of 10 divided by log of 2. Okay, and then equals, I get 3.32192809.5. Okay, now, so what does that mean? If we take this number, which again is rounded, and we go all the way back here, that means that 2 raised to that power equals 10. Okay, was it 10 that I used? Yes. Now, this number has been rounded off by the calculator, and the more I round it off, the less accurate it's going to be. But let's just say 3.32. So 2 to the 3.32 power, what do we get? 2 raised to the 3.32 power, and I get 9.9866, which is close to 10. And again, the more of this number I use, the closer to 10 I'm going to get. But the point is, I'm now able to take a log with any acceptable base. Remember, the base has to be greater than 0. And we're taking the log of a number that has to be greater than 0. Even if it's not base 10 or base e, we can change it using the change of base formula, punch it into our calculator. Let's go back and redo this same problem, only now we're going to use log base e. So if x equals log base 2 of 10, I could rewrite that as log base e of 10 over log base e of 2, which of course I would write like this. Oops, no I wouldn't. Slow down. It'd be natural log of 10 over natural log of 2. In other words, rather than write log base e, I'd write natural log. If I put in the natural log of 10 divided by the natural log of 2, I get the same number that I got here, okay? But the point is these two bases, when you split it up, they have to both be base 10 or both be base e. Don't have one of them 10 and one of them e or vice versa. They've got to both be 10 or both be e, and then that will give you the solution. Okay, so let's take a look at some examples from the textbook of that. And here we go. All right, so log base 3 of 7. It says use the change of base formula to find each logarithm to 4 decimal places. So this would be the log of 7 over the log of 3, which is log of 7 divided by log of 3, approximately 1.7, let's see, it said to 4 places, 1.77124, which would round down, so 1.7712. Again, I want to point out that instead of using base 10, I could have used base E, and that would have given me the same result. Again, the 1.7712 rounding to the 4th decimal place. Okay. Let's see here. How about this? Log base 1/2 of 6. So that will be common log or log base 10 of 6 over the log base 10 of 1/2. And let's see what we get there. The log of 6 divided by the log of 1/2. I'm getting negative 2.58496. So rounding there, that would round up. We'd get negative 2.5850. Again, if I use natural log of 6 over natural log of 1/2, I'd get the same answer. How about this one? The log base pi of E. So that would be the natural log of E over the natural log of pi. And again, I could have used base 10. I just chose to use base E for this example. And so on the calculator, the natural log of E, well, my graphing or my scientific calculator doesn't have a button that just says E. So I've got the natural log, and then I had to use the second function key and get E to the X. So what am I going to put in there so that it's just E? Well, E to the 1 power would be E. So I'll put a 1 in there. Okay, so the whole thing looks like that. Okay, I've got 2 sets of parentheses, 1 set around my 1 and 1 set around the thing I'm taking the log of. All of that over the natural log of, okay, so divided by natural log of pi. All right, where is pi? Well, on my scientific calculator here, I have a button that says pi. It's right there. And if you have a different scientific calculator, you might have to look around for it to find it. Okay, I'll close that up and push equals. And let's see what I'm getting. I'm getting 0.87356 on and on. The 6 would round up, so 0.8736. All right. Anyway, so that's how you use the change of base formula. We're going to go on now to section 11.7. Okay. So let's see here. All right. We're going to look at some equations. It says solve each equation. The first example is this. 6 to the x minus 2 power equals 36. Recall earlier in the chapter, we had a situation where we said if the bases were equal, then the exponents would be equal as well. So if I could rewrite this equation so that the bases were the same, the exponents would be equal. Well, I can take 36 on the right side of the equal sign and write it as 6 squared. 36 equals 6 squared. So now 6 to the x minus 2 power equals 6 to the 2 power, which means, since the bases are the same, the exponents are equal, which gives us the equation x minus 2 equals 2. Adding 2 to both sides of this equation, we get x equals 4. Let's check our work. If x is 4, we'd have 6 to the 4 minus 2 power equals 36, which would be 6 squared equals 36. 36 equals 36, and the solution checks. All right, let's take a look at another example. 3 to the x plus 1 power equals 27. Well, again, if I could get the same base on both sides of the equation, I could set the exponents equal to each other. 27 is 3 cubed. So now, since the bases are the same, x plus 1 equals 3. Subtracting 1, x equals 2. Let's check our work. 3 to the 2 plus 1 power equals 27. 3 to the 3 power equals 27. 27 equals 27, and it checks. Let's look at one that's a little more difficult. This says 8 to the negative 2x plus 1 power equals 1 over 64. So again, I need to have the same base. Well, on the left side, I've got 8. On the right side, 64 is equal to 8 squared, isn't it? So I could write it like that. But I don't want 1 over 8 squared. I want 8 to some power. But isn't that equal to 8 to the negative 2 power? Now, granted, I know we're used to taking something with a negative exponent and rewriting it with a positive exponent. But in this case, we want to get the same bases. So here, 8 to the negative 2 plus x, 8 to the negative 2x plus 1 equals 8 to the negative 2 power. Therefore, negative 2x plus 1 equals negative 2. Solving for x, subtract 1 from both sides. Divide both sides by negative 2. X equals 3/2. Well, let's check our work. Let's see. 8 to the negative 2 times 3/2 power plus 1 equals 1 over 64. 8 to the, let's see, negative 2 times 3/2 would be what? Negative 3. So negative 3 plus 1 is negative 2. 8 to the negative 2 is 1 over 8 squared, which is 1 over 64 equals 1 over 64. So again, the solution checks. All right, well, this is all great. And when we have an equation where we can rewrite it so that the base is the same on each side, then we can take the exponents and set them equal to each other in an equation form. But what about this example? 4 to the x power equals 5. I have no idea how to take 5 and write it as 4 to some power, or how to take 4 and write it as 5 to some power. So this method that I've been using isn't going to work in this situation. So I need to use a different method here. Well, what I'm going to do, I'm going to take this exponential equation and change it into a logarithmic equation. So we're going to have log base 4 of 5 equals x. Okay, the base is the same, but the players change places. I'm going to rewrite that like this. X equals log base 4 of 5, because I want to have that log base 4 of 5 on the right side of the equation. Now I'm going to use the change of base formula. I use base 10. So I can rewrite it like that. And that I can put into my calculator. And it says give an exact solution and an approximation to 4 decimal places. So the exact solution would be this or that. And then the decimal approximation, let's see, we've got log of 5, close it up, divided by log of 4, close it up. I get 1.160964047. And again, it's set to 4 decimal places. So let's see, that's going to be here. The 6 is going to round up. So 1.1610, because the 6 will round 9 up to a 10. So we get that answer. Okay, let's take a look at another example of that. Let's say we've got 5 to the x plus 1 power equals 3. Well, here again, I don't know how to take 3 and write it as 5 to some power, or 5 and write it as 3 to some power. So I'm going to change this exponential equation into a logarithmic equation. So I'm going to get log base 5 of 3 equals x plus 1. And again, I'm going to rewrite that so that I've got x on the left and my log expression on the right. Okay. Well, I'm going to need to subtract 1 from both sides of the equation. So I've got x equals -1 plus the log base 5 of 3, which is -1 plus, I'm going to use natural log this time, natural log of 3 over natural log of 5. Okay, so I've got -1 plus the natural log of 3 divided by the natural log of 5. And I get -0.317393806. So the 9 would round up and we'd have that. Okay. Now, I wrote it this way. I also could have said natural log of 3 over natural log of 5 minus 1. If I do that, though, make sure that I separate this. It's not included as part of the natural log of 5. Okay, it's a separate term. So be careful there. All right, let's look at some examples involving e. Let's say we have this problem. E to the 2.9x power equals 4.5. Again, I have no idea how to write 4.5 as e to some power. So I'm going to use changing this into a logarithmic equation. So this is going to be log base e of 4.5 equals 2.9x. But log base e is just natural log. So that's the natural log of 4.5 divided by equals 2.9x. Getting ahead of myself there, because the next step, we're going to divide both sides by 2.9. So x equals the natural log of 4.5, that whole thing divided by 2.9. Natural log of 4.5, close it up, divided by 2.9, 0.51864738. Rounding here, the 4 rounds down. And so we get approximately that. Okay, let's see here. Now, let's say we have this equation. The log of 2x equals 4. I think I said this the other day, but if not, I'll say it again, or I will say it again. When you're solving an exponential equation, there's a high probability that you're going to change it into a logarithmic equation to solve it. If you're solving a logarithmic equation, most likely you're going to change it into an exponential equation to solve it. Here we have a logarithmic equation. I want to remind you that this is log base 10. If I rewrite this as an exponential equation, it would look like this. 10 to the 4th power equals 2x. Then dividing by 2, x equals 10 to the 4th power over 2. Well, 10 to the 4th power would be 10,000. Divided by 2 would be 5,000. So x equals 5,000. Let's take a look at another example. Log base 4 of 2x minus 1, the quantity, equals 3. Changing this logarithmic equation into an exponential equation, we would get 4 cubed equals 2x minus 1. Well, 4 cubed, 4 times 4 is 16, times 4 is 64. So we get 64 equals 2x minus 1. We'll add 1 to both sides. 65 equals 2x. We'll divide both sides by 2. X equals 65 over 2. Okay. let's see here, which is also what? 32.5. A question came up earlier today from a student, and I want to remind you, they said, what do you do if you're putting, it's not this particular one, but let's say you've got something like 8.3 repeating. How do you enter that into WebAssign? Don't. This would be like 8 1/3, which would be 25 thirds. So don't use repeating decimals. There's a way to do it, but it's kind of tricky. Don't use mixed numbers. Use improper fractions. And don't round unless it tells you to. Okay. Anyway, let's see here. Here we go. Let's say I've got log of 3 minus 2x equals log of x plus 24. Well, just like if we have a base raised to a power equals the same base to a power, the powers are equal. If we're taking log base 10 of a quantity equals log base 10 of another quantity, then those two quantities must also be equal. Again, recall that these are both log base 10. So now with this equation, I'm going to solve for x. I'll subtract x from both sides. 3 minus 3x equals 24. Subtract 3 from both sides. Negative 3x equals 21. Divide by negative 3x equals negative 7. Let's check our work. Log of 3 minus 2 times negative 7 equals log of negative 7 plus 24. Let's see. 3 minus 2 times negative 7 is 3 plus 14 is 17. And negative 7 plus 24 is 17. I don't need to know what the log of 17 is. I know that it's real. And the log of 17 equals the log of 17. So the answer checks. Okay. Now, I want to look at a couple of formulas. Before we do that, I want to talk about the idea of half-life. Okay, so half-life. If there, that's supposed to be a hyphen there. If there is a material that is decaying according to some half-life situation, it means that after a certain length of time, it loses half of its material. And then after that same length of time, it loses half of that material. And after the same length of time, it loses half of that material. Let's just say, for instance, I have 128 Snickers bars. And I put them in a refrigerator, and I come back 1 week later, and I discover that half of them are gone. There's only 64 of them. And then I come back 1 week later, and I discover that half of those are gone. There's only 32 of them. And I come back 1 week later, and there's only 16 of them. And then 1 week later, there's 8 of them, and then there's 4 of them, and then there's 2, and then there's 1, and then there's a half, and then there's a quarter, and this goes on and on and on. Each time a week goes by, half of what was there at the beginning of that week disappears. So we'd say that the half-life of these Snickers bars is 1 week. Notice that as we keep cutting in half, a fourth, an eighth, a 16th, a 1/32nd, it's never going to reach 0. It's going to get closer and closer and closer to 0, but in theory, it wouldn't reach 0. Okay. Now, if we have the exponential equation in the form y equals 1/2 to the x power, I believe we looked at that the other day, and what we get is an exponential function that's decreasing, okay? It looks something like that. All right, now, there's a formula for half-life, and the formula looks like this. Let's see here, 2. It says A equals A sub 0 times 2 to the negative t over h power. All right, now, A sub 0 is the original amount at the beginning of the problem. A is the ending amount, so we'll say original, ending. T is time, and h is the half-life of whatever substance that is. Now, I just got done looking at this example where I said for the half-life, we'd have to have a 1/2 as a base. But this formula is written where there's a 2 as a base. So how does that work out? Well, let's go back to this. Y equals 1/2 to the x power, okay? What if instead I had y equals 2 to the x, all right? Well, that would be what? Doubling, right? But what if I had y equals 2 to the negative x? That's the same thing as y equals 1/2 to the x, which is the same thing as y equals 1 to the x over 2 to the x, or 1/2 to the x power. My point is this. This formula, by using a 2 and a negative t, it's the same thing as if we wrote it like this. Okay, 1/2 is the base with a positive t. But that's not the way the book presents the formula. So I'm going to go with what the book does, but just realize that because of that negative exponent, it's like we're halving or cutting things in half. Okay. So again, we've got this formula, a equals a sub 0 times 2 to the negative t over h power. Okay, let's take a look at a problem. It says tritium, and I don't know if I'm saying that correctly or not. I'm not a chemistry major. Tritium decay. The half, or maybe it's tritium. The half-life of tritium is 12.4 years. So the half-life is 12.4 years. How long will it take? So time is the question mark, for 25% of a sample of tritium to decompose. All right, so they haven't told us how much we've got. We're going to start out with some amount we're going to call a sub 0, okay? What they do tell us, though, it says, how long will it take for 25% of the sample to decompose? Well, we're starting with a sub 0, and 25% of that is going to go away. So we're going to end up with 75% of the amount we started with. 75%, 3/4, 0.75, okay? So the ending amount, A, is 75% of the starting amount. This way, I don't need to know the specific starting amount, and I can still solve the equation. So using this formula, we're going to put 0.75 a sub 0 in the place of a. A sub 0 is going to stay as a sub 0 times 2 to the negative t over 12.4 years power. Okay, now we're trying to solve for t. T is in an exponent form. So we're going to need to change this into a logarithmic equation. But before we do, we've got to get rid of that coefficient out in front, the a sub 0. So what I'm going to do is I'm going to divide both sides of the equation by a sub 0, which gives me that. 0.75 equals 2 to the negative t divided by 12.4 power. Now it's in a form that I can convert it into a logarithmic equation. Log base 2 of 0.75 equals negative t over 12.4. Okay. I need to get rid of the negative sign in front of the t, and I need to get rid of the 12.4. So I'm going to multiply both sides of this equation by negative 12.4. The negative will get rid of the negative in front of the t, and the 12.4 will clear the fraction on the right side. So now I've got negative 12.4 log base 2 of 0.75 equals t. I'm going to rewrite that again with t on the left side, and I'm going to get negative 12.4 log base 2 of 0.75. All that's left to do is I'm going to use the change of base formula. So it's going to become negative 12.4 times the log of 0.75 divided by the log of 2. I'm going to punch all that into my calculator. Okay, so negative 12.4 times the log of 0.75, close that up with parentheses, divide by the log of 2, close that up with parentheses, and I get 5.146464991. And let's see, they rounded to the nearest tenth of a year. So they said about 5.1 years. Okay, let's take a look at another example. This one says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. So again, we're going to use this half-life formula. Okay. We know that the time is 2 years. It says 20% of a radioactive element decays. So we don't know the starting amount. We're just going to call it A sub 0. But the ending amount, if 20% decays, I have 80% remaining. Okay. So the ending amount A is 80% of the beginning amount A sub 0. And I could just write it 0.8. I don't need that 0 there. Okay. We're supposed to find its half-life. So substituting the place of A, 0.8 A sub 0 equals A sub 0 times 2 to the negative 2 divided by H power. Just like in the last problem, we need to get rid of the A sub 0 on both sides of the equation. So dividing it out, we get 0.8 equals 2 to the negative 2 over H power. Now it's in a form where we can change it to a logarithmic equation. Log base 2 of 0.8 equals negative 2 divided by H. Now we need to be careful. We're trying to solve for H. H is in the denominator and I need to get it in the numerator. So the next thing I'm going to do is multiply both sides by H. So now I've got H log base 2 of 0.8 equals negative 2. Okay. Then I'm going to divide both sides by log base 2 of 0.8. So that gives me, I'm going to go to the next page. That gives me H equals negative 2 divided by the log base 2 of 0.8. Okay. Using the change of base formula, I get this. Okay. So I've got negative 2 divided by, and then I'm going to put this whole thing in parentheses. So then the log of 0.8 divided by the log of 2, and then parentheses around that whole thing. So negative 2 divided by parentheses log of 0.8 divided by log of 2. Close that entire thing up, and I get 6.2125, etc. And they say about 6.2 years. So they rounded to the 10th of a year. Okay, let's see here. There's another formula that they give in this section, and this is P equals P sub 0 e to the kt power, where P is a population at some time T, P sub 0 is the initial population at T equals 0, and K depends on the growth rate. All right. Really, if you think of this problem, A equals P e to the RT power, very similar, very similar. The interest rate, so to speak, the growth rate, starting amount, ending amount, ending amount. So it really accomplishes the same thing, okay? But taking a look at this formula, let's see here. All right, it says compound interest. If $500 is deposited into an account paying 8.5% annual interest, compounded semi-annually, How long will it take for the account to increase to $800? I just introduced this new formula, but this problem, it says compounded semi-annually. So it's not compounded continuously. So what formula are we going to use? This one, A equals P times 1 plus R over K to the KT power, where K in this case stands for the number of compoundings. So the key word there is the lack of continuously, where it says semi-annually. All right. So the principal is $500. The interest rate is 8.5% or 0.085. The compounding semi-annually is 2, and time is the unknown. So using this formula, A equals $500 times 1 plus 0.085 over 2 raised to the 2t power. Something's missing. Oh, here's what's missing. They told us, how long will it take for the account to increase to $800? Yeah. We had to have more information that I forgot to read. Okay. So let's see, what can we do with this thing? Well, we're trying to solve for t, which is the exponent. So let's see, can I simplify what's inside? If I take 0.085 divided by 2, I get 0.0425. And then I can add 1 plus 0.0425 is going to be 1.0425, and that's all to the 2t power. Okay. I'm trying to solve for an exponent. I could change it into logarithmic form, but first I've got to get rid of that leading coefficient. So let's divide both sides by 500. And we get what? 8/5 equals 1.0425 to the 2t power. Okay? Which means log base 1.0425 of 8/5 equals 2t. Okay. Well, we could divide both sides by 2, or how about if we multiply both sides by 1/2? Same thing. So now, in fact, let's change 1/2 to 0.5. So I got 0.5 log base 1.0425 of 8/5 equals t. And why did I use a half instead of dividing by 2? And why did I change it from 1/2 to 0.5? Just to make it easier to put in the calculator. So now I've got t equals 0.5 log base 1.0425 of 8/5 using the change of base formula. I'm going to have this massive thing. Isn't that fun? Fun for whom, you say? Okay, so 0.5 times the log of 8/5, close that up, divided by the log of 1.0425, close that up, and I get 5.64614. Let's see here. Maybe I can write that so that it's actually legible. You just never know. Miracles do happen every day. All right, 5.646140295. And let's see, they said about 5.6 years. So I don't even know if you remember the original problem back here. The key was it said it was compounded semi-annually. Okay. All right, let's see here. Take a look. How are we doing for time? We got time for one more. This says population growth. The population of a city is expected to triple every 15 years. When can the city planners expect the present population of 140 persons to double? You know what? We're going to skip that one. We're going to skip that one. I know you're thinking, why did I even bring it up? Well, we don't need to go there. So, reminder, tonight you've got 11.6, change of base formula, 11.7, and the chapter review. Tomorrow, we're going to review for the test on Tuesday. This afternoon, I won't be here for the office hour, but if you have questions, email me. I'll get back to you when I can. No class on Monday, okay? Tuesday, you're going to take your chapter 11 test. And then we'll spend the rest of next week reviewing for the final. All right, and with that, I bid you adieu.